21, 2793 2798. Brannan, G.D., Setzer, C.S., and Kemp, K.E. 2001. Effectiveness of rinses in AL. Vioting bitterness and astringency residuals in model solutions. J. Sens. Stud. 16. 261275. Brochet, F., and Duberdew, D. 2001. Wine descriptive language supports cognitive specificity of chemical senses. Brain Language 77, 187196. Brossard, C., Rousseau, F., and Dumont, J.P. 2007. Perceptual interactions between characteristic notes smelled above aqueous solutions of odorant mix. Tures. Chemistry. Senses 32, 319327. Bucking, M. 2000. Freisetzung von Aromastoffen in Gegenwart retardierender Substanzen AUSDEM Kaffeegetränk. Ph.D. Thesis, University of Hamburg, Germany, reported in Prinz, J.F., and de Wijck, R. 2004. The role of oral process. Sing in flavor perception. In flavor perception. A. J. Taylor and D. D. Roberts. eds. Blackwell Publishing, Oxford, UK. Buettner, A. 2004. Investigation of potent odorants and after-odor development in 2 Chardonnay wines using the buccal odor screening system, Boss. J. Agric. Food Chemistry. 52, 2339 2346. Buettner, A. Beer, A. Hanig, C., and Settles, M. 2001. Observation of the swallowing process by application of videofluoroscopy and real-time magnetic resonance imaging, consequences for retronasal aroma stimulation. Chemistry. Senses. 26, 1211 1219. Carvalho, E., Matus, N., Platt, B., Pionit, I., Dufuk, E., and de Freitas, V. 2006. Influence of wine pectic polysaccharides on the interactions between condensed tannins and salivary proteins. J. Agric. Food Chemistry. 54, 8936 8944. Colliner, A. E., Adams, D. O., and Noble, A. C. 2004. Comparison of procedures for reducing astringency carryover effects in evaluation of red wines. Ost. J. Grape Wine Res. 10, 2631. Datt, Ella, Jones Gottman, M., Zator, R.J., and Evans, A. C. 1998. Human brain function during odor encoding and recognition, a PET activation study. Ann. N. Acad. SCI. 855, 572574. Chapter 1, Introduction 22. Datt, Ella, Zator, R.J., and Jones Gottman, M. 2002. Olfactory Learning, Convergent Findings from Lesion and Brain Imaging Studies in Humans. Brain 125. 86101. Depp, M., Knecht, S., Lohmann, H., Fleischer, H., Heindel, W., Ringelstein, E.B. and Henningsen, H. 2000. Assessment of hemispheric language lateralization. A comparison between fMRI and FTCD. J. Sereb. Blood flow metab. 20-263268. De Wijck, R. Engelen, L. and Prins, J. F. 2003. The role of intraoral manipulation in the perception of sensory attributes. Appetite 40, 1-7. Fisher, C., Fisher, U., and Jacob, L. 1996. Impact of matrix variables, ethanol, sugar, glycerol, pH and temperature on the partition coefficients of aroma compounds in wine and their kinetics of volatilization. Proc. 4th int. Simp. Cool CLI. Mate Vitic. Inall, Rochester, NY, July 16-20, 1996. T. Hennickling T. E. Wolf. And E. M. Harkis, eds. pp. 742-46. NY State Agricultural Experimental Station, Geneva, New York. Frank, R. Gusteland, R.C., Bailey, J., Rybalski, K., Seiden, O., and Dulé, M.F. 2006. Characterization of the sniff magnitude test. Arch. Attila in Gaul. Head. Neck Sug. 132, 532-536. Goyert, H., Frank, M.E., Gent, J.F., and Hettinger, T.P. 2007. Characteristic. Component odors emerge from mixtures after selective adaptation. Brain res. Bull. 72, 19. Hayashi, N., Ujihara, T., and Kohata, K. 2005. Reduction of catechin astringency by the complexation of gallate-type catechins with pectin. Biozi. Biotechnol. Biochem. 69, 1306 1310. Hers, R.S., McCall, C., Cahill, L. 1999. Hemispheric lateralization in the process. Sing of odor pleasantness versus odor names. Chemistry. Senses 24, 691695. Hollowood, T.O., Linforth, R.S.T., and Taylor, A.J. 2002. The effect of viscosity on the perception of flavor. Chemistry. Senses 28, 1123. Jackson, R.S. 2000. Wine Science, Principles, Practice, Perception, 2nd ed. Academic Press, San Diego, CA. Jackson, R.S. 2008. Wine Science, Principles and Applications, 3rd ed. Academic Press, San Diego, CA. Kent, P.F., Moselle, M.M., Murphy, S.J., and Hornung, D.E. 1996. The interaction of imposed and inherent olfactory mucosal activity patterns and their composite representation in a mammalian species using voltage-sensitive dyes. J. Neurosci. 16, 345353. Kilcast, D., and Clegg, S. 2002. Sensory perception of creaminess and its relation ship with food structure. Foodquill. Pref. 13, 609623. Necht, S., Drager, B., Depp, M., Bub, L., Lohmann, H., Flohl, A., Ringelstein, E.B. and Henningsen, H. 2000. Handness and hemispheric language dominance in healthy humans. Brain 123, 2512 2518. Kuznicki, J.T., and Turner, L.S. 1986. Reaction time in the perceptual processing of taste quality. Chemistry. Senses 11, 183201. Lang, D.G. 1982. Characterization of human behavior during odor perception. Perception 11, 221230. Lang, D.G. 1983. Natural sniffing gives optimum odor perception for humans. Perception 12, 99117. References 23. Lang, D.G. 1986. Identification of single dissimilar odors is achieved by humans with a single sniff. Physical. Behave. 37, 163-170. Lang, D.G., Link, C., Jinks, A.L., and Hutchinson, I. 2002. The limited capacity of humans to identify the components of taste mixtures and taste-odor mix. Tools. Perception 31, 617635. Lawless, H.T., and Ingen, T. 1977. Associations of odors, interference, mnemon. ICS and verbal labeling. J. Expt. Psychol. Human Learn. Mem. 3, 5259. Lehrer, A. 1975. Talking about Wine. Language 51, 901923. Mainland, J. and Sobel, N. 2006. The sniff is part of the olfactory percept. Chemistry. Senses 31, 181196. Marshall, K., Lang, D.G., Jinks, A.J., Effendi, J., and Hutchinson, I. 2005. Perception of temporal order and the identification of components in taste mixtures. Physical. Behave. 83, 673681. Matus, N., Carvalho, E., Luss, C., and De Freitas, V. 2004. Influence of the tannin structure on the disruption effect of carbohydrates on protein tannin aggregates. Anal. Jim. Acta 513, 135140. Mojit, J. and Costa, E.P. 2005. Sensory memory and food texture. Food quill. Brief. 16, 251266. Murphy, C., Kane, W.S., and Bartoshuk, L.M. 1977. Mutual action of taste and olfaction. Sense. Process. 1, 204211. Murray, J.E. 2004. The Ups and Downs of Face Perception, Evidence for Holistic Encoding of Upright and Inverted Faces. Perception 33, 387398. Nigoas, S., Vicious, R., Belridge, O., and Hummel, T. 2008. New Ways to Understand Aroma Perception. Food Chemistry. 108, 1247 1254. Normand, V., Avison, S., and Parker, O. 2004. Modeling the Kinetics of Flavor. Release during drinking. Chemistry. Senses 29, 235245. Paynord, E. Trans by M. Scuster, 1987. The Taste of Wine. The Art and Science of Wine Appreciation. MacDonald and Company, London. Pierce, J., and Halpern, B.P. 1996. Orthonasal and retronasal odorant identification based upon vapor phase input from common substances. Chemistry. Senses. 21, 529543. Prescott, J. 1999. Flavor as a Psychological Construct, Implications for Perceiving and Measuring the Sensory Qualities of Foods. Foodquill. Brief. 10, 349356. Prescott, J., Johnston, V., and Francis, J. 2004. Odor-taste interactions, effects of attentional strategies during exposure. Chemistry. Senses 29, 331340. Pridmore, R.W., Hitters, R., Melgosa, M., and Niguirula, I. 2005. Discussion on perceived and measured wine color. Color res. Apple. 30, 146152. Robichaud, J.L., and Noble, A.C. 1990. Astringency and bitterness of selected phenolics in wine. JSCI. Food Agric. 53, 343353. Ross, C.F., Hinken, C., and Weller, K. 2007. Efficacy of palate cleansers for reduction of astringency carryover during repeated ingestions of red wine. J. Sens. Stud. 22, 293312. Skolton, P. 1987. How much do judges absorb? Wines Vines 69, 3, 2324. Chapter 1, Introduction 24. Small, D.M., Gerber, J.C., Mc, Y.E., and Hummel, T. 2005. Differential neural responses evoked by orthonasal versus retronasal odorant perception in humans. Neuron 47, 593605. Sobel, N., Kahn, R.H., Hartley, C.A., Sullivan, E.V., and Gabrieli, J.D.E. 2000. Sniffing longer rather than stronger to maintain olfactory detection threshold. Chemistry. Senses 25, 18. Sobel, N., Prabhakaran, V., Desmond, J.E., Glover, G.H., Good, R.L., Sullivan, E.V. and Gabrieli, J.D. 1998. Sniffing and smelling, separate subsystems in the human olfactory cortex. Nature, 392, 282286. Van der Klaw, N.J., and Frank, R. 1996. Scaling component intensities of complex stimuli, the influence of response alternatives. Environ. Int. 22, 2131. Wildhuizen, M.G., Bender, G., Constable, R.T., and Small, D.M. 2007. Trying to detect taste in a tasteless solution, modulation of early gustatory cortex by attention to taste. Chemistry. Senses 32, 569581. Zhao, K., Scherer, P.W., Hahilu, S.O., and Dalton, P. 2004. Effect of anatomy on human nasal airflow and odorant transport patterns, implications for olfaction. Chemistry. Senses 29, 365379. References 25. This page intentionally left blank. Visual perceptions. Chapter contents. Color 27. Color perception and measurement 27. Significance in tasting 32. Origin and characteristics 34. Clarity 41. Crystals 41. Sediment 42. Proteinaceous haze 43. Phenolic haze 43. Cas 43. Deposits on bottle surfaces 44. Microbial spoilage 44. Viscosity 45. Spritz 46. Tears 48. As noted in Chapter 1, wine appearance can provide useful indicators of quality, style, and varietal origin. Unfortunately, it can also provide false clues and prejudice assessment. In this chapter, the nature, origin, and significance of the visual aspects of wines are more fully investigated. Color. Color perception and measurement. The visual characteristics of a wine depend on how its chemical and particulate nature transmit, absorb, and reflect visible radiation, about 300 to 700 nm. For example, the pigments in red wine reflect, and absorb, specific wavelengths. Their reflection and transmission of primarily long wavelengths. Chapter 2. 27. Wine Tasting, a Professional Handbook, 2nd edition. Copyright #2009 by Academic Press, Incorporated. All rights of reproduction in any form reserved. Induce reactions in the retina that are interpreted by the brain as red. The color intensity and hue of the wine depend on the amount and chemical state of the pigments present, and correspondingly the quantity and quality of light reflected. Color purity depends on the relative absorptive properties of the pigments across the visible spectrum. The broader the spectrum, the less pure the perceived color, indicated by a higher tint value in Fig 2.1. Although such characteristics can be accurately measured with a spectrophotometer, the relevance of the data to human color perception is far from simple. Spectrophotometric measurements assess the intensity of individual wavelengths, whereas human perception combines the responses from many neurons, cones and rods, in the retina. The 6 to 7 million cones are densely arranged in the central portion of the retina, with the nearly 120 million rods positioned on the walls of the eye surrounding the cones. The number and distribution of the types of cones are distinct, as is their range of sensitivity. The least common, S, are those that respond with a peak sensitivity in the short, blue, wavelength region. Far more common are cones responding optimally in the middle and long wavelength regions, respectively termed L and M cones. Although there is considerable variation in their proportion among individuals, it does not appear to markedly affect color perception. Brainard et al., 2000. The pigments in the latter two cone types, L and M, show considerable overlap in their absorption spectra. In contrast, the rods react primarily to low-intensity light of medium to short wavelength, and respond relatively slowly to intensity change. Color perception results from the combined impulses from the three types of cones, whereas brightness and clarity are the prerogative of the rods. In addition, the eye possesses additional receptor cells, P and M, that help coordinate the stimuli from the rods and differentiate contrast. Finally, color perception involves a comparison of the nerve responses at the boundary where color changes. This probably is the origin of the relative constancy in color. Figure 2.1. Absorbance scans of a single cultivar port. Turiga National, 1981. At different ages, from Backer and Timberlake. 1986, reproduced by permission. Chapter 2, Visual Perceptions 28. Perception that occurs under most daily changes in sunlight spectral quality. Brewitt al., 1986. Thus, color perception of natural objects is a learned construct from multiple stimuli, not a simple reaction to individual wave lengths or their respective intensities. Kaiser and Boynton, 1996, Squire. It al., 2008. There is no generally accepted classification of wine color. It is also notoriously difficult to adequately represent the color of wine on photographic paper or film. Although people can differentiate thousands of color gradations by direct comparison, they tend to consistently differentiate comparatively few by name. Fig 2.2. Many terms are used synonymously. Chapanis, 1965. Therefore, it is probably best to keep the number of color terms limited and simple to facilitate consistent use. Color terms ideally should incorporate aspects of hue, wavelength, purity, saturation, grayness, and brightness, capacity to reflect or transmit light. However, their typical integration reflects the difficulty people have in differentiating these aspects. For example, brown commonly would be described as a hue. Technically, however, yellow-red is a hue, precise region along the visible spectrum, whereas brown is an impure yellow-red, combining yellow-red and blue spectral elements. Equally, moderate pink is partially saturated red. Figure 2.3 illustrates the three recognized color attributes: hue, saturation, and brightness. The availability of a standard for wine colors would increase the value of color in sensory evaluation. The Munsell color notation, Munsell, 1980, has a long history of use in the food industry and scientific investigation. However, it does not fully represent the range of human color vision. Genetic variability in color perception also limits its applicability as a standard. Color blindness is the best known example, but more subtle deficiencies are widespread. Color perception also changes with age. Yellow pigment accumulates in the lens and retina, resulting in a slow loss in blue sensitivity, while difficulties remain in correlating spectral absorbency to perceived color. CUNY 2002, simple techniques can often yield useful data. For example, the color of red wines is often assessed by its absorbency at 420 nm and 520 nm, Summers and Evans, 1977. Figure 2.2 Coefficients of consistency for the selections made to 233 color names, from Chapanis, 1965. Color 29. The sum of these values is a measure of color depth, density, while their ratio estimates tint, hue, absorbency. At 420 nm provides an indicator of a brownish cast, while absorbency at 520 nm assesses redness. As red wines age, the level of yellowish polymeric pigments increases, and the impact of monomeric red anthocyanins decreases. Young red wines often have ratios of 0.4 to 0.5, whereas old reds frequently show values in the range of 0.8 to 0.9. An alternate method incorporates absorbency at 620 nm. Glories, 1984. Problems associated with turbidity may be adjusted for by measurements taken at 700 nm. Mazur et al., 1999, or following. Sample centrifugation, Bus, 2007. Additional information may be derived from estimates of the proportion of colored, ionized, monomeric anthocyanins, total anthocyanin and phenol contents. The proportion of anthocyanins complexed to various phenolic polymers can be derived from acidification with hydrochloric acid, decolorization with metabisulfite, and subsequent recoloration with acetaldehyde, respectively, Summers and Evans, 1977. Because the proportion of complexed anthocyanins increases with age, it has been described as the wine's chemical age. Several studies have shown a strong correlation between the amount of colored, ionized, anthocyanins and the perceived quality of young red wines. Summers and Evans, 1974, Summers, 1998. Despite these adjustments, these measures do not represent the presence of important red pigments such as pyrantoanthocyanins. In addition, besides the resulting shift toward brown, aging of red wines is associated with pigment loss and reduction in color depth. In white wines, absorbency is typically measured at 420 nm. It is used to give an indicator of browning, Fig 2.4, to facilitate assessing the color of bottled wines. Skouramounis et al., 2003, have developed a means of spectrophotometrically assessing the degree of browning in situ. As with PURP, LE, BL, UE, GREEN, YE, LLO, W, GR, EENORANG, E, yellow, black, white, blue, brightness, green, red, saturation. Figure 2.3 Schematic representation of the psychological dimensions of color space, from Chapanis, 1965. Chapter 2, Visual Perceptions 30. Simple color measurements in red wines. The values derived may, however, miss subtleties that may be important. Skouramounis et al., 2005. Another means of objectively assessing wine color employs tristimulus colorimetry. It involves taking 3 separate intensity measurements of light transmitted through wine, using red, green, and blue filters. This approximates the response of the human eye. Appropriate measurements may be obtained with a spectrophotometer, but require complicated mathematical transformations. Tristimulus colorimeters directly translate the reading into tristimulus measurements. Estimates of brightness, light/dark, saturation or chroma, degree of grayness, and hue, basic color, are generated. These are the three parameters normally used in defining color. However, the most accurate means of measure in wine color is to assess absorbency over the full range of the visible spectrum. The CIE lab system designed by La Commission Internationale de l'Éclairage uses these measurements to derive values for L, relative lightness, A, relative redness, on a red-green axis, and B, relative yellowness, on a yellow-blue axis. The values are typically calculated with software packages that accompany the spectrophotometer. The calculations approximate human color vision, where lightness is largely derived from a selective combination of L and M cone inputs, and hue derived from comparison of impulses from L and M cones, red-green axis, and a comparison of impulses from S cones with the sum of L and M responses, blue-yellow axis, Gigenfertner and Kipper, 2003. CIE lab measurements can also be used to derive the values required to reproduce color using software such as Adobe W, Photoshop W, L, luminosity, C, chroma, a half, C, a quarter, A, 2B2, P, and H, hue, H equals tan 1, A/B. Hue often reflects the dominant wavelength of the light, but not consistently. For example, a yellow color may originate from light in the yellow range, or a combination of light in the red and green ranges. CIE lab measurements have been used to measure wine color, though several researchers have proposed changes to make the values more applicable. BLE to wine, Niguirula et al., 1995, Ayala et al., 1997. The information is particularly suited to determining color differences. This information can improve the blending of wines to a predetermined color, Niguirula et al., 1990, but has found little use in wine assessment. Perez Magarino and 175. 50%. Assessors 25. 0. 0.050.10. Browning, a 420. 0.150.200.250.30. Figure 2.4% of 31 assessors rating wines with various levels of browning as visually unacceptable, from Peng et al., 1999, reproduced by permission. Color 31. Gonzalez San Jose, 2002, have proposed simple absorbance measurements to predict CIE lab values for wineries, without the equipment and software normally necessary. One of the problems in associating such measurements with human perception relates to the marked differences in how assessments may be conducted. In spectrophotometric measurements, wines, often diluted, are placed in cuvettes, usually 1 or 2 mm for undiluted red wine, or 10 mm if diluted. In contrast, visual evaluation of wine occurs in a glass under poorly regulated light conditions. In the latter situation, there can be considerable light scattering and marked differences in color noted as the depth of the wine changes on slanting the glass. These differences have recently been described analytically by Hitters et al. 2003. Finally, different combinations of pigments in various stages of oxidation and polymerization may give rise to the same subjective color impression. an alternative technique for color assessment being investigated is digital photography. By computerized assessment of the image, pixel by pixel. Better correlation with human perception has been reported. Pointer et al., 2002, Brosnan and Son. 2004, Chung et al., 2005. Digital photography is less expensive than the purchase and operation of a spectrophotometer, is easier to use, assesses a larger surface area, useful where the color is non-homogeneous, is rapid, and the data can easily be transferred to a computer for analysis. Yam and Papadakis, 2004, Leon et al., 2006. An example of digital camera analysis used to evaluate wine color is given by Martin et al., 2007. Significance in tasting. Color often affects quality perception, Fig 2.5. Fig 2.6, as well as taste and odor perception. Mager, 1974, Clydesdale et al., 1992. For red wines, flavor intensity and wine quality has been correlated with color density, Island and Marquise. 1993, and hue, the proportion of red ionized anthocyanins, Summers and Evans, 1974, Buscelli and Gigliotti, 1993. Wine flavors, located primarily in the skins, are likely to be extracted under the Figure 2.5 illustration of the relationship between wine quality assessed by smell and taste, blind, and by sight alone, color, from Tromp and Van Wyk, 1977, reproduced by permission. Chapter 2, Visual Perceptions 32. Same conditions that promote pigment extraction. Color depth is also considered an indicator of aging potential. Occasionally, wines are sampled in black wine glasses, or under low-intensity red light, to obviate any possible color bias. Color is such a critical element in sensory memory that identification may become markedly distorted without it. For example, people usually correctly identify cola-flavored beverages when colored dark brown, but frequently misidentified the solution as orange or tea when it was colored orange. Sakai et al., 2005. In another example, cherry-flavored beverages were frequently misidentified as lime when colored green. Dubose et al., 1980. In wine, the influence of color has been clearly demonstrated by Morit et al., 2001. The addition of tasteless anthocyanin, red, pigments to a white wine induced tasters to describe the wine in terms typical of a red wine, objects of a red or sombre color. This distortion may be less pronounced with expert tasters, at least when the color seriously conflicts with other sensory attributes. Parr et al., 2003. In the Morit study, the white wine, Sauvignon Blanc, that had been colored red, has several aromatic similarities to Cabernet Sauvignon, wines of which the enology students frequently sampled. Color depth has also been shown to enhance perceived flavor intensity. Zellner and Whitten, 1999. The influence has even been observed at the neuronal level. Osterbauer et al., 2005. showing a color typically associated with a particular fragrance. For example, red with strawberry enhances the response in the orbitofrontal complex. This is the cerebral region known to integrate sensory impulses. The reverse occurs with inappropriate colors, for example, blue with strawberry. That this influence is not just a laboratory phenomenon is indicated by the effect of an oxidized color on wine quality, Fig 2.5, and acceptability, Fig 2.6. Although wine color can affect wine assessment, not all tasters are equally influenced. Williams et al., 1984b. Interestingly, this feature A. B. Figure 2.6 relation between flavor and odor acceptance A, and color and flavor acceptance B, from Pocconi et al. 1998, reproduced by permission. Color 33 seemed to be independent of taster experience. This may relate to the manner in which tasters assess the wines. It is known from other studies on sensory interaction, taste or taste odor, that these influences are most marked when assessments are requested to be holistic, and least evident when assessments are conducted attribute by attribute. Specific directions. To ignore color in assessment may result in tasters disregarding color in their evaluation. Williams et al., 1984a. Consumers and tasters alike usually come to associate particular colors with certain wines. For example, young dry white wines generally range from nearly colorless to pale straw-colored. A more obvious yellow tint may suggest long maceration or maturation in oak cooperage. More golden colors often arise following prolonged maturation in oak barrels, extended bottle aging, or indicate the presence of a sweet botrytis wine. Sherries vary from pale straw to dark golden brown, depending on the style. Finos the lightest, Olorosos the darkest. Rose wines are expected to be pale to light pinkish rose-colored, without shades of blue. Red wines vary from deep purple to tawny red. Initially, most red wines possess a purplish red hue, especially noticeable at the edge of the glass. Subsequently, the wine loses its color depth and increasingly takes on a brickish hue. Red ports, depending on the style, may be deep red, ruby, or tawny colored. Because all wines eventually take on brownish hues, browning is often used as an indicator of age. This feature is indicated by a lowering of the E420/E520 spectrophotometric ratio, Summers and Evans, 1977. However, a brownish cast may equally indicate oxidation or heating. Therefore, wine age, type, and style must be known before interpreting the meaning and significance of a brownish hue. Brown shades are acceptable only if associated with the development of a desirable processing or aged bouquet. The heating of Madeira, which gives the wine its brown coloration and baked bouquet, is an example of a process-produced browning. Because most wines fail to develop a desirable aged bouquet, brown casts often mean that the wine is oxidized or over the hill. Origin and characteristics. Red wines. Anthocyanins are the primary determinants of color in red grapes and wine. In grapes, anthocyanins occur predominantly as glucosides. These are conjugates with one or more glucose molecules. The complex increases both chemical stability and water solubility. The glucoside may also associate with acetic, coumaric, or caffeic acids. 5 classes of anthocyanins occur in grapes: cyanins, delphinins, malvins, ponins, and petunins. They are differentiated based on the number. Chapter 2, Visual Perceptions 34. Of hydroxyl and methyl groups on the B ring of the anthocyanidin molecule. Table 2.1. The content and relative amounts of each class vary. Consider ably between cultivars and with growing conditions. Wenzel et al., 1987. The hydroxylation pattern of the B ring primarily controls color, hue and stability. Free hydroxyl groups enhance blueness, whereas methylation augments redness. In addition, the presence of 2 hydroxyl groups next to each other on the B ring, eaudiphenols, markedly enhances their potential to oxidize. Thus, wine with a high proportion of malvin or ponin, neither of which possesses eaudiphenols, significantly enhances color stability. Resistance to oxidation is also a function of conjugation of the anthocyanin with sugar and other compounds. Robinson et al., 1966. In most red grapes, malvin is the predominant anthocyanin. Because it is the reddest of anthocyanins, the red hue of most young red wine comes from this compound. Besides the 5 main types of anthocyanins, each type occurs in a dynamic equilibrium among 5 major molecular states. 4 are free forms, and 1 is bound to sulfur dioxide, Fig 2.7. Most are colorless within the pH range of wine. Those that exist in the flavolium state generate a red hue, while those in the quinoidal state give a bluish tint. The proportion of each state depends primarily on the pH and sulfur dioxide content of the wine. Low pH enhances redness, favors the flavolium state, whereas high pH generates a blue-mauve cast, by favoring the quinoidal state. Table 2.1. Anthocyanins occurring in wine. Specific name R3, R4, R5. Cyanidin 00. Ponidin ARC3O. Delphinidin 000. Petunidin ARC300. Malvidin ARC30 ARC3. Derivative structure. Monoglucoside R1 and a quarter glucose, bound at the glucose 1 position. Diglucoside R1 and R2 and a quarter glucose, bound at the glucose 1 position. Source: After Methods for Analysis of Musts and Wines, Emma Amarine and C.S. Orff, copyright 1980 John Wiley & Sons, Incorporated. Reprinted by permission of John Wiley & Sons, Incorporated. Color 35. Color density is also affected. Bleaching of anthocyanins by sulfur dioxide, either due to addition or production by yeasts during fermentation, can diminish color depth. In grapes, anthocyanins exist primarily in stacked conglomerates. These occur primarily as hydrophobic interactions between individual anthocyanins, self-association, or between anthocyanins and other phenolic compounds, copigmentation. Both complexes increase light absorbency and color density. During vinification and maturation, these conglomerates tend to dissociate. Anthocyanin molecules freed into the acidic wine environment lose their bluish color. In addition, dissociation results in reduced. Figure 2.7. Equilibria among the major forms of anthocyanins in wine. Gl. Glucose, from Jackson. 2008, reproduced by permission. Chapter 2, Visual Perceptions 36. Light absorption and loss in color depth. Typical losses in color density can vary from 2 to 5-fold, depending on the pH, ethanol, and tannin contents of the wine. Nevertheless, sufficient copigmentation complexes may survive and form during fermentation to contribute to the purple tint characteristic of most young red wines. These color changes occur without a reduction in the absolute anthocyanin content. During maturation, not only do anthocyanin aggregates dissociate, but individual anthocyanin molecules tend to lose their sugar and acyl, acetate, caffeate, or coumarate constituents. This makes them both more susceptible to irreversible oxidation, browning, as well as conversion of the colored flavolium state to colorless hemiacetals. To limit these events, it is important that the wine contain significant quantities of flavonoids, catechins, proanthocyanidins, dimers, trimers, and tetramers of catechins, and their polymers, condensed tannin. These combine with free anthocyanins to form stable polymers. The polymers also extend light absorption into the blue region. This partially explains the brownish shift that occurs during aging. The concurrent extraction of flavonoids with anthocyanins during fermentation is crucial to long-term color stability in red wines. These compounds begin to polymerize with free anthocyanins almost immediately. By the end of fermentation, some 25% of the anthocyanin content may exist polymerized with tannins. This can rise to about 40% within 1 year in oak. Cooperage, Summers, 1982. Subsequent polymerization continues more slowly, and may approach 100% within several years, Fig 2.8. Thus, red color reflects not only the amount, nature, and states of the anthocyanin in wine, but also the types and amounts of flavonoids extracted and retained during and after vinification. Jackson, 2008. The poor color stability of most red muscadine wines appears to derive from the absence of appropriate tannins and acylated anthocyanins in muscadine grapes. Sims and Morris, 1986. A somewhat similar situation with Pinot Noir may explain the generally poor coloration of its wines. Polymerization protects the anthocyanin molecule from oxidation or other chemical modifications. Incidentally, polymerization also increases solubility, minimizing both tannin and pigment loss by precipitation. In addition, more anthocyanin molecules are in a colored state in tannin. Figure 2.8 increase in the contribution of polymeric pigments to wine color density during the aging of Shiraz wines. Mean values, extremes. From Summers, 1982, reproduced by permission. Color 37. Complexes, due to increases in the proportion of both flavolium and quinoidal states. For example, about 60% of anthocyanin tannin polymers are colored at pH 3.4, whereas 20% of equivalent-free anthocyanins are colored. Fig 2.9. The yellow-brown flavolium and quinoidal anthocyanin tannin polymers are generally thought to irritate most of the age-related brackish shades. Polymerization of anthocyanins with flavonoids occurs slowly in the absence of oxygen. Nevertheless, polymerization is promoted during maturation by the oxygen inadvertently absorbed during racking. This has led to the development of microoxygenation systems to provide the winemaker with control over the rate and degree of oxygenation, especially when using inert cooperage. The small amounts of peroxide generated as oxygen reacts with tannins oxidizes ethanol to acetaldehyde. The subsequent reaction between acetaldehyde and anthocyanins promotes their polymerization with flavonoids. The initially small anthocyanin acetaldehyde flavonoid polymers are thought to enhance the violet shift so typical of young red wines. Dallas et al., 1996. Acetaldehyde also reacts with sulfur dioxide, removing it from anthocyanins. This not only reverses the bleaching action of sulfur dioxide, but also liberates the anthocyanin for polymerization with proanthocyanidins. Other mechanisms suspected in color stabilization involve various yeast metabolites, notably pyruvic acid. It can react with anthocyanins, Fulkrand et al., 1998, generating a tawny red color. Monoglucosides and cumroyl. Monoglucosides of Malvin, the predominant anthocyanin in grapes, may also complex with 4-vinyl-phenol, generating red-orange pigments, Fulkrand et al., 1997. These and related compounds are termed pyranoanthocyanins. For details, see the recent review by Renskit et al. 2007, or Jackson 2008. In addition, internal rearrangements of anthocyanins and other flavonoids produce yellow-orange xanthillium products. Colorless flavonoids also generate brownish products upon oxidation. Thus, although the color of red wines starts out primarily produced by anthocyanins, the aged color of red wines is a complex of anthocyanin tannin polymers, oxidized 150 0% A 150 0 123 pH 4-5% B A plus AOH TAOH TA plus TAO AO. Figure 2.9 Equilibria among different forms of A. Free anthocyanins and B. Combined anthocyanins, TA, extracted from wine. Red flavolium cation, O, colorless carbinol. Pseudobase, O, blue-violet quinoidal base, from Ribéreau Guéon. And Glories, 1987, reproduced by permission. Chapter 2, Visual Perceptions 38. Tannins, pyranoanthocyanins, and xanthillium products and polymers. Its complexity is such that even more sophisticated analytical instruments than currently exist may be needed to discover the critical and decisive events involved in the evolution of wine color. Table 2.2 highlights some of the various forms producing yellow, yellow-red, yellow-brown, red, and violet shades. The reduction in color density that also accompanies aging results from oxidation, structural changes in anthocyanin tannin polymers, and their precipitation with tartrate salts or soluble proteins. Red wines can vary from deep red-purple to pale tawny red. As noted, the purplish-red hue of young red wines may be due to the continuing presence of anthocyanin complexes and anthocyanin acetaldehyde flavonoid polymers, but may also indicate that the wine's pH is undesirably high, 3.8. A light color may indicate grape immaturity or poor winemaking practices. However, certain cultivars, such as Gomery and Pinot Noir, seldom yield wines with deep colors. Spätburgunder wines from Germany are typically so pale as to often resemble a dark rose. Cool climatic conditions are not conducive to the production of dark-colored red wines. In these situations, the varietal origin must be known to avoid unduly penalizing the wine. More intensely pigmented varieties, such as Shiraz and Cabernet Sauvignon, may remain deep red for decades. Dark shades often correlate with rich flavors. These are probably extracted along with anthocyanins from the skins, because older vinification procedures favor the uptake of high levels. Table 2.2 Color and molecular weight of some wine phenols. NAMEB color molecular weight, K. The A red 500 AOH non-colored, AO violet, Azo 3 non-colored, P non-colored 600, T yellow 1000 2000, TA red 1000 2000 TAOH non-colored, TAO violet, TAzo 3 non-colored, TC yellow red 2000 3000, TTC yellow brown 3000 5000, TP yellow 5000. Source: A from Ribéreau Guéon and Glories, 1987, reproduced by permission. BA, anthocyanin, P, procyanidin, T, tannin, TC, condensed tannin, TTC, very condensed tannin, TP. Tannin condensed with polysaccharides, O, carbinol pseudobase, O, quinoidal base, HSO3, bisulfite. Addition compound. Color 39. Of tannins, they generate bitter /astringent sensations that can take decades to soften. This can be avoided by modern techniques, notably treatments such as the use of rotary fermenters. These favor the early extraction of berry flavors and intense coloration, before tannin uptake reaches high levels. Even with standard fermenters, shorter skin contact time during fermentation can generate milder but still highly flavored, deeply colored wines. Most red wines begin to take on a noticeable brackish cast within a few years, especially when long aged in oak cooperage, Fig 2.1. Brackish or tawny red colors are acceptable only if associated with the development of a favorable aged bouquet. In most standard red wines, these hues indicate only that the wine has lost the fruitiness it might have had. In young red wines, brick shades may suggest overheating, as in a warehouse where it might be associated with a baked odor, or a faulty closure, and associated with an oxidized odor. Rose wines. Rose wines are expected to be pale pink, cherry, or raspberry colored, with shades of blue. The actual shade depends on the amount and type of anthocyanins found in the cultivar used. An orangish cast is generally undesirable, but can be characteristic of some roses made from Grenache. Otherwise, hints of orange usually suggest oxidation. Purplish hints often signify that the wine is too high in pH and may taste flat. White wines. In comparison with red wines, little is known about the chemical nature and development of color in white wines. The small phenolic content of white wines consists mostly of hydroxycinnamates, such as caphteric acid, and related derivatives. On crushing, these readily oxidize and form S-glutathionyl complexes. These generally do not turn brown. Thus, it is believed that most of the yellowish pigmentation in young white wine is derived from the extraction and oxidation of flavonols, such as quercetin and kaempferol, non-flavonoids and lignins extracted from oak cooperage, if used, can add to the color of white wines. The deepening yellow gold of older white wines probably comes from the oxidation of phenols or galac turenic acid, a breakdown product of pectins from grape cell walls. However, gold shades may also develop following the formation of mel-anoidin compounds by Maillard reactions, or the caramelization of sugars. Occasionally, a pinkish cast is detectable in some white wines. For example, the pinking of Sauvignon Blanc wines derives from the incidental oxidation of dehydrated leucoanthocyanins, flavin 3,4-diols. However, the pinkish Chapter 2, Visual Perceptions 40. Coloration of some Gewürztraminer wines comes from trace amounts of anthocyanins extracted from the skins of pinkish-red clones of the cultivar. Some so-called white, blush, wines, such as white Zinfandel, come from red grapes pressed early to minimize color extraction. In fortified sweet wines, much of the color comes from either oxidation of phenolics in the wine, or from melanoid pigments formed during heating of the wine or in concentrating grape juice used for sweetening. Typically, young, dry, white wines range from nearly colorless to pale straw. A more obvious yellow tint may be considered suspicious, unless associated with extended skin contact, maceration, or maturation in oak cooperage. The wine takes on deeper hues with aging. If associated with the development of an appreciated aged bouquet, it is desirable. If associated with accidental oxidation and the presence of an oxidized odor, it is unacceptable. In contrast, unusually pale colors may suggest the use of unripe grapes, absence of typical coloration, high acidity, little varietal character, removal of the juice from the skins without maceration, extraction of few phenolics and reduced varietal flavor, or the excessive use of sulfur dioxide, which has a bleaching action. Sweet white wines generally are more intensely colored, being straw yellow to yellow gold. This may result from in-berry oxidation of grape constituents during overripening. Sherries vary from pale straw to golden brown, depending on the particular style, fino to oloroso, and the degree to which they are sweetened. Madeiras are always amber-colored, unless decolorized, due to the heat processing they undergo. Although white wines typically darken with age, some fortified white wine may lighten, for example, Marsala. This results from the precipitation of melanoid pigments. Clarity. In contrast to the complexity of interpreting the significance of color, haziness is always considered a fault. With modern techniques of clarification, consumers have come to expect a clear product with long shelf life. This does demand considerable effort to achieve. Crystals. Young wines typically are supersaturated with tartrate salts after fermentation. During maturation, Isomerization of these salts reduces solubility. Consequently, storage under cool conditions often leads to crystallization. Crusty, flake-like crystals are usually potassium butatrate, whereas fine crystals are typically calcium tartrate. Clarity 41. As the alcohol content rises during fermentation, the solubility of bitter trait decreases. This induces the slow precipitation of potassium butatrate. Cream of tartar. Given sufficient time, the salt crystals precipitate spontaneously. In northern regions, the low temperatures found in unheated cellars can induce adequately rapid precipitation. Where spontaneous precipitation is inadequate, refrigeration often achieves rapid and satisfactory butatrate stability. Because butatrate crystallization is concentration dependent, mildly unstable wines may be insufficiently stabilized by cold treatment. Protective colloids, such as yeast mannoproteins, may retard crystallization by mask. In positively charged sites on butatrate crystals, Lubbers et al., 1993. The interaction between tannins, tartrate, and potassium ions also retards crystallization. Occasionally, crystals of calcium oxalate form in wine. If crystallization occurs, it develops primarily in older wines due to the slow oxidation of ferrous oxalate to the unstable ferric form. After dissociation from the metal, oxalic acid may bond with calcium, forming calcium oxalate crystals. Other potential troublesome sources of crystals are saccharic and mucic acids. Both are produced by the pathogen Botrytis cinerea and may form insoluble calcium salts. Calcium mucate is often the source of the yellowish particles occasionally found in bottles of Sautons. Although comparatively rare, the presence of tartrate salt crystals is not a legitimate cause for consumer rejection. The crystals are tasteless and usually remain in the bottle with any sediment that may have developed during aging. Alternatively, tartrate crystals may form on the cork. Because white wines are transparent and sold in pale to colorless bottles, crystals are more obvious in white than red wine. In addition, white wines are typically chilled or stored cool, accentuating crystal formation. Some producers mention their possible occurrence by the euphemistic term wine diamonds. Consumers have been known to unwittingly mistake elongated tartrate crystals for glass slivers. Sediment. Resuspension of sediment is probably the most frequent source of clouding. In older red wine, sediment typically consists of a complex of polymerized anthocyanins, tannins, proteins, and tartrate crystals. Depending on their chemical composition, sediment may have a bitter or chalky taste. To some wine aficionados, the presence of sediment is considered a sign of quality. Excessive and unnecessary clarification can remove flavorants, but its avoidance does not guarantee a finer or more flavorful wine. Chapter 2, Visual Perceptions 42. Proteinaceous haze. Although an uncommon source of wine rejection, protein haze can still cause considerable economic loss in bottle returns. Proteinaceous haze results from the clumping of dissolved proteins into light dispersing particles. Its formation is enhanced by the presence of sulfites, heating, and the presence of tannins and trace amounts of metal ions. Proanthocyanins, oligomers of catechin flavonoids, bind well with proteins containing proteins Line, Sabbat, 2006. However, these typically precipitate during fermentation, maturation, or fining. Thus, they are not the problem they can be in. Beer, Azano et al., 1984. The proteins that appear to be the principal source of problems in bottled wine are the pathogenesis-related, PR, proteins. Chitinase, and acid-stable thaumatin-like proteins, Waters et al., 1996b. Dambruch et al., 2003. They occur in infected grapes and are also produced rapidly in grapes damaged during harvesting, Pocock and Waters. 1998. Although yeast manna proteins and grape arabinogalactan protein complexes may promote heat-induced protein haze, specific members can also reduce its formation. Pellerin et al., 1994, Dupin et al., 2000. Phenolic haze. Excessive use of oak chips in wine maturation or the accidental incorporation of leaf material during grape crushing, Summers and Z. Emleys, 1985. Can occasionally induce rare forms of phenolic haze. The first situation results from the excessive extraction of ellagic acid, leading to their formation of fine, off-white to fawn-colored crystals. Fine, yellow, quercetin crystals, extracted from leaf material during crushing, can induce a flavanol haze in white wines. This is particularly likely if the wine is bottled before the crystals have had a chance to settle sufficiently. Summers and Z. Emleys, 1985. The excessive use of sulfur dioxide has also been associated with cases of phenolic haze in red wines. Cas. Several insoluble metal salts can generate haziness in bottled wine. Cas. The most important are induced by iron, Fe3 and Fe2, and copper, Cu2 and Q, ions. The primary source of troublesome concentrations of these metal ions comes from corroded winery equipment. Two forms of ferric Cas are recognized. White wines may be affected by a white haze that forms as soluble ferrous phosphate oxidizes to insoluble ferric phosphate. The haze results either from particles of ferric phosphate alone or from a complex formed between ferric phosphate and soluble clarity 43. Proteins. In red wine, oxidation of ferrous to ferric ions can generate a blue Cas. In this instance, ferric ions form insoluble particles with anthocyanins and tannins. In contrast to iron-induced haziness, copper Cas forms only under reduced, anaerobic conditions. The Cas develops as a fine, reddish-brown deposit when the redox potential of bottled wine falls during aging. Expo. Sure to light speeds the reaction. The particles consist of cupric and cuprous sulfides, or their complexes with proteins. Copper Cas is primarily a problem in white wines but can also occur in rose wines. Deposits on bottle surfaces. Occasionally, sediment adheres tightly to the inner surfaces of the bottle. This can generate an elongated, elliptical deposit on the lower side of the bottle. Less frequently, a lacquer-like deposit may form in bottles of red wine. It consists of a film-like tannin anthocyanin protein complex. Waters et al., 1996a. Champagne bottles may also develop a thin, film-like deposit on its inner surfaces. This phenomenon, called mask, results from the deposition of a complex between albumin, used as a fining agent, and fatty acids, probably derived from autolysing yeast cells. After the second, in-bottle fermentation, Morgenit al. 1978. Microbial spoilage. Haze can also result from the action of spoilage organisms, yeasts and bacteria. The most important spoilage yeasts in bottled wine are species of Zygosaccharomyces and Brettanomyces. 3 groups of bacteria may be involved: lactic acid bacteria, acetic acid bacteria, and Bacillus species. Zygosaccharomyces bailey can generate both flocculent and granular deposits. Rankine and Pylone, 1973, notably in white and rose wines. Contamination usually results from growth in improperly cleaned and sterilized bottling equipment. In contrast, Brettanomyces spp induces a distinct Has-iness. It may become evident at less than 10 cells/ml, Edelanii, 1966. With other yeasts, noticeable cloudiness begins only at concentrations above 10 cells/ml. Yeast-induced haziness may occur without spoilage, but frequently is associated with vinegary, Z. bailey, or mousy, barnyardy. Brettanomyces, Ophodus. Other fungi can cause clouding or pellicle formation, but only under aerobic conditions, a situation not found in properly sealed bottled wine. Certain lactic acid bacteria generate a cloudy, viscous deposit in red wines, a situation called tone. The affected wine also turns a dull red-brown, develops a sauerkrauty or mousy taint, and may show spritz if. Chapter 2, Visual Perceptions 44. Carbon dioxide accumulates. Other strains may synthesize profuse amounts of mucilaginous polysaccharides, B1,3 glucans. These polysaccharides hold the bacteria together in long silky chains. The filaments often appear as floating threads, generating the condition called ropiness. When dispersed, the polysaccharides give the wine an oily look and viscous texture. Although visually unappealing, ropiness is not consistently associated with taints. Acetic acid bacteria have long been associated with wine spoilage. For years, molecular oxygen was thought essential for their growth. It is now known that quinones, oxidized phenolics, can substitute for oxygen. Aldecreus, 1986. Thus, acetic acid bacteria may grow in bottled wine if acceptable electron acceptors are present. In addition, even trace amounts of oxygen incorporated in procedures such as racking or batonnage can activate growth. If they multiply in wine, they can form a haziness associated with the development of vinegary odors and tastes. Lactic acid bacteria can induce a diversity of spoilage problems, usually in wine at high pH values, 3.7. If this occurs in bottled wine, their growth can lead to the development of slight haziness. Viscosity. The viscosity of wine is an in-mouth perception, largely dependent on its sugar, ethanol, glycerol, and soluble polysaccharide contents. If mentioned, it is usually due to obvious reduced fluidity. This is discernible only at unusually high sugar and / or alcohol contents, when glycerol content exceeds 25 g/liter, as in botrytis wines, or in the presence of mucopolysaccharides produced by bacteria, in cases of wines showing ropiness or tone. Although glycerol has usually been mentioned in relation to increased Wine viscosity, lower sugar contents, 15g fructose/5g glucose, can generate about the same degree of perceived viscosity as 25g glycerol, Nergal and Pickering, 2005. At these concentrations, viscosity values reach about 1.5 cp. MPa. At and above this level, detectable difference begins to become perceptible. Besides affecting fluidity, viscosity at or above 1.5 cp reduces the perception of astringency and sourness. Smith and Noble, 1998. It may also reduce the perceived intensity of aromatic compounds. Cook et al., 2003. However, the latter phenomenon appears to occur at the viscosity values typical of food or desserts, not wine. Thus, its potential real relevance may relate more to how wine pairs with food than on the perception of wine itself. Viscosity 45. Spritz. Still wines may retain sufficient carbon dioxide after fermentation to form bubbles along the sides and bottom of the glass. This usually occurs if the wine is bottled early, before supersaturated carbon dioxide in the wine has escaped. This is not uncommonly seen in bottles of Beaujolais Nouveau and some young white wines. Bubbles may also come from carbon dioxide produced by bacterial metabolism. This may develop as a consequence of malolactic fermentation occurring after bottling. Producers apply various procedures to prevent this from occurring. It is associated with the formation of a fine, haze-producing sediment. Light spritz may also result from the action of spoilage bacteria, as in the case of wine showing tone. In most instances, marked effervescence is intentional. The size, association, and duration of bubbling are considered important quality features in sparkling wines. Slow, continuous effervescence is favored by prolonged contact between yeast lees and the wine. After several months, yeast's autolysis, self-digestion, releases cell wall constituents, colloidal manoproteins, into the wine. The weak bonds formed between carbon dioxide and these proteins are thought essential to the production of a steady stream of bubbles following opening. Whether the sound of bursting bubbles has sensory significance to the perceived quality of sparkling wines, as it does in carbonated beverages, Zampini and Spence, 2005, has yet to be studied. Many factors affect the solubility of carbon dioxide. Primary among these are temperature and the wine's sugar and ethanol contents. Increasing these factors decreases gas solubility. Once the wine is poured, atmospheric pressure becomes the critical factor promoting bubble formation. Pressure on the wine drops from 6 atm in the bottle to 1 atm ambient. This reduces carbon dioxide solubility from about 14 g/liter to 2 g/liter. This initiates the release of approximately 5 liters of gas from a 750 milliliters bottle. In the absence of agitation, there is insufficient free energy for the CO2 to escape. Immediately, it enters a metastable state from which it is slowly liberated. Carbon dioxide escapes from the wine by several mechanisms. Fig 2.10. The initial foaming associated with pouring is activated by free energy liberated by pouring. Pouring also generates microbubbles that slowly escape. However, the continuous chains of bubbles, so desired in sparkling wine, are produced by heterogeneous nucleation. Most bubbles develop as carbon dioxide diffuses into microscopic gas pockets in fibrous contaminants on the sides of the glass. This particulate material usually consists of cellulosic fragments left following glass drying, or that have fallen out of the air as dust, Ligable et al., 2002. Those few bubble. Chapter 2, Visual Perceptions 46. Chains that form in the body of the wine probably originate from microgas pockets associated with minute-suspended crystals of potassium butatrate, or cellulosic fragments. Gas pockets in these particles probably form during the initial burst of homogeneous fizzing that occurs as the wine is poured into the glass. As the bubbles are released and begin to rise, they enlarge, and their physical dispersion becomes more pronounced. The slow, progressive release of bubbles is the principal, and desirable, means by which CO2 escapes from the wine. In contrast, gushing, the sudden to explosive release of carbon dioxide, results from a number of separate processes. Mechanical shock waves or rapid pouring provides sufficient energy to weaken the bonds between water and carbon dioxide. As bubbles reach a critical size, they incorporate more CO2 than they lose, enlarging as they rise. In addition, semi-stabilized to stabilized microbubbles, previously generated in the bottle, are ready to enlarge explosively if sufficient free energy is provided. Another important feature in assessing the quality of sparkling wine is the accumulation of a small mound of bubbles on the surface of the wine. In the center of the glass, mousse, and a ring of bubbles, cordon de mousse. Along the meniscus, at the air-wine glass interface. Prolonged duration of the mousse, as in the head-on beer, is undesirable. The durability of these formations is largely dependent on the nature of surfactants, such as soluble proteins, polyphenols, and polysaccharides. They decrease surface tension, easing bubble fusion. This results as gravity removes fluid from between the bubbles, inducing them to fuse and take on angular shapes. As their size increases, so does their tendency to break. Figure 2.10 Mechanisms of effervescence, CO2 escape, from sparkling wine, from Jackson, 2008. Reproduced by permission. Spritz 47. Natural surfactants originate as degradation products of yeast autolysis. Their concentration in the wine increases 2 to 3 times within the first year of maturation, following the second CO2-producing fermentation. Contaminant surfactants, notably soap or detergent residues left after glass washing, can effectively dampen bubble formation. These residues coat the particles that are essential for the initiation, nucleation, step in bubble formation. This can be readily demonstrated with a washed but poorly rinsed champagne flute. Tears. Droplets form and slide down the sides of the glass after swirling. Fig 2.11. These have been variously termed tears legs or rivulets. They form when alcohol evaporates from the film of wine, coating the inner surfaces of the glass. Because ethanol volatilizes more rapidly than water, the surface tension of the film increases. This induces water molecules in the film to pool together more tightly, resulting in droplet formation. As their mass increases, the droplets start to sag, producing arches. Finally, the drops slide down, form in the tears. On reaching the surface of the wine, fluid is lost and the drop may pool back. Without repeated swirling, the rim of the film slowly descends, eventually reaching the level of the meniscus around the sides of the glass. After swirling, the increased surface tension of the film, created by alcohol evaporation, may induce wine to flow up the sides of the glass. Neogi, 1985. In addition, cooling produced by alcohol evaporation activates the generation of convection currents that facilitate this flow. The duration of tears formation depends on factors affecting the rate of evaporation, such as temperature, alcohol content, and the liquid forward/air interface. Movement of wine up the sides of the glass can be demonstrated by adding a drop of food coloring, or non-wettable powder such as lycopodium powder, to wine after tears have begun to form. Contrary to common belief, glycerol neither significantly affects nor is required for formation of tears. Figure 2.11 illustration of the flow of wine up a wine glass, lower arrows, and the formation of tears. These begin to flow down the sides as ethanol escapes from the thin film of wine adhering to the glass, upper arrows, that results in an increase of surface tension of the remaining water. Chapter 2, Visual Perceptions 48. Suggested readings. Clydesdale, F.M. 1993. Color as a Factor in Food Choice. Crit. Revelation. Food SCI. Neuter. 33, 83101. Hutchings, S. 1999. Food Color and Appearance. Aspen, Gaithersburg. Ligabulair, G. 2002. The Science of Bubbly. SCI. 228, 1, 8085. Schwartz, S.H. 2004. Visual Perception, 3rd ed. McGraw-Hill Medical, New York. Walker, J. 1983. What causes the tears that form on the inside of a glass of wine? SCI. 248, 162169. Waterhouse, A.L., and Kennedy, J. eds. 2004. Red Wine Color. Revealing the Mysteries. ACS Symposium Series, number 886. American Chemical Society Publi. Cation, Washington, D.C. References. Aldecreus, P. 1986. Oxygen Supply to Immobilized Cells. 5. Theoretical Calculations and Experimental Data for the Oxidation of Glycerol by Immobilized Gluco-Nobacter oxidans cells with oxygen or p-benzoquinone as electron acceptor. Biotechnol. Bioeng. 28, 223232. Amarine, M. A. and Orff, C.S. 1980. Methods for Analysis of Musts and Wines. John Wiley, New York. Asano, K., Otsu, K., Shinagawa, K., and Hashimoto, N. 1984. Affinity of proanthocyanidins and their oxidation products for haze-forming proteins of beer, and the formation of chill haze. Agric. Biol. Chemistry. 48, 1139 1146. Ayala, F., Eshavari, J.F., and Niguirula, I. 1997. A new simplified method for measuring the color of wines. 2. White wines and brandies. J. in all. Vitic. 48, 364369. Backer, J., and Timberlake, C.F. 1986. The mechanism of color changes in aging. Port wine. J. in all. Vitic. 37, 288292. Bus, M.J. 2007. The color of red wine. Ph.D. Thesis, School of Agriculture. Food and Wine, University of Adelaide, Australia. Brainard, D.H., Reorder, A., Yarmorky, Y., Calderon, J.B., Mether, A., Neitz, M. Neitz, J., Williams, D.R., and Jacobs, G.H. 2000. Functional consequences of the relative numbers of L and M cones. J. Opt. Soc. A 17, 607614. Brosnan, T., and Son, D.W. 2004. Improving Quality Inspection of Food Products by Computer Vision. J. Food Engine. 61, 316. Brew, P., Sciuscia, T.R., Linden, L., and Letvin, J.Y. 1986. The Colors of Things. SCI. Amer. 255, 3, 8491. Buselli, P., and Giliotti, A. 1993. Importanza di alcuni parametri analitici nella valutazione dell'attitudine all'invecchiamento dei vini. Inotecnico 29, 5, 7584. Chapanis, A. 1965. Color Names for Color Space. Scientist 53, 327345. Chung, V., Westland, S., Lee, C., Hardeberg, J., and Connor, D. 2005. Characterization of trichromatic color cameras by using a new multispectral imaging technique. J. Optic. Soc. A 22, 1231 1200